Thank you, Bob. Hi, everyone. Hope you had a good lunch, nice coffee. So, yes, I am from AXA. I just wanted to know with my audience who knows AXA. Okay. So you probably know, yes, AXA is an insurance company, and you probably have a lot of products from us. I work in the research department, applied research, and today I want to talk to you exactly about the risk intelligence. What does that mean, and how different products enable it? First, a bit about AXA for those 2 or 3 who don't know it is that we're quite a big company. We serve over 108 million customers in 54 countries, and we have over 100,000 employees. So keep those numbers in mind. I don't want to test you afterwards, but just to have an idea of the scale, you know. And specifically today, it will be about AXA XL, which is our corporate branch. Okay, they insure over 8 million locations over the whole world. And this is what makes it interesting. When you as a person take an insurance, such as for example motor insurance, it's quite easy. You give away your risk of having a car crash, and then we insure that. In case something happens, we can cover for it. Now when a commercial client comes to us, such as a large fast food chain, it's not that easy. This risk could be very complicated. We are asked to insure anything from factories to office buildings to storefronts. And not only that, but when they subscribe, when you sign it off, we realize there are maybe a few thousand locations spread over the country or the whole world. So it's a big challenge to take on. This is what is the risk, and then the intelligence of this risk today looks a bit like this. In the financial industry, we all work with data sheets, right? So it's not that easy to understand what you are actually signing off when you say, okay, I want to insure this large chain. There are some data. We usually have addresses. We sometimes have some number of buildings or the stories that each building has, but not too much, and it's not fully filled. One that is interesting, however, is the location. So we're provided with the location of this part, which gives us some kind of understanding. Today, this location is a point. It may then help us say, okay, how far are we from the river to see if there is a risk of being flooded, right? In this case, it's relatively far. Depending on the relief, there may be a flood or not. However, my colleagues, software engineers, did a super good job at integrating with various data sources to understand more than just a point, to understand the whole footprint around that location. So this client, for example, we can see its footprint in yellow over the satellite image. And not only it has a very large area, but most of the value is concentrated in the blue buildings, which are then very close to the river and have very high risk of flood. Now, super interesting, but we want to get in even more details, okay? Not just around the location, but what is onto this location. So taking one from this list, then we have a risk engineer that inspects it. Before COVID, they used to go on site to see what kind of factors there are. Today, they look at a satellite image. With the footprint, they can say, okay, this is the building of interest. We don't have to look at the one on the left or on the bottom. And then what can we see on this building? Well, we could see, for example, that this particular building on the south is fully covered by solar panels. In case of a hail, then it would provide big damage and may also interrupt the power to the building. Similarly, the building in the west, then if we zoom in, we see it has some cooling towers next to it, which spread across the whole building. So in case of a failure, the whole cooling system could present a risk to business interruption. And one of the biggest risks is present in the north of the campus, where we see there are some fuel tanks. In case of a spark or something, there could be a big explosion with risk even to human life. So risk engineers are interested in knowing about all these things, and not only they want to know about them on a specific location, but when presented with a list of the whole chains, they want to be able to prioritize them according to these risks. Today they do it by value, tomorrow they want to do it by these risks exactly. So not necessarily to look at the largest site or the most valuable one, but at the ones that make sense. So how do we get there? And I'm super glad we're today in AI and industry talk, because then we have a very important conundrum. Do we buy a solution or do we make it? And I think many people in the industry are faced with this. And one thing we found is that sometimes when the problem is quite common, but it also provides some value and it's complex to solve, then there is somebody who's doing it. There is usually a startup, you've seen many of them in the other floor, who provide a specific solution for this, or even big players. For example, there is Munich Re, who provides a service for understanding damage after a hurricane. And for this, we would be super happy to buy this service directly. We are sure they know what they do, and they do a very good job. But sometimes we may not have the solution. And this could be because the models are quite accessible. Convolutional neural nets are, I don't know, bread and butter today. Everyone can train one. It's just a matter of finding the right data sets. So I went online and I searched for satellite-related data sets, found 123 of them. So all good and fine, then we can build our model, sometimes. In our case, however, we're in this case, meaning we start from scratch. Maybe some of you have been in this situation. We need to collect the data first, and only then we can build the model. And why? Because we like doing model science or data science? Not necessarily. It's mostly because we are actually needing a lot of subject matter expertise. Similar to healthcare, where you need the surgeons who are trained, same, these people are risk engineers. They need to know exactly what is happening on that location. So what is our data then? Why is it so special? And here I have some examples, more than what we've looked before. We have provided an interface to extract this knowledge from the risk engineers that is similar to Google Maps, and they can just annotate on top. So like the blue rectangle would be cooling towers, the pink ones would be silos, and then they can do this for different locations in their portfolio. So while they work, while they inspect all these locations, they're also providing us with important data that we can use to train our algorithm. Now, one thing to be careful of is that this data needs to be very well defined, okay? So I want to focus your attention a little bit to the image on the right and to ask the question, what is a skylight? They want to look for skylights in this image. And you may be tempted to say, well, these ones are skylights. They are transparent structures that provide natural light inside the building. But already there is the question, what about the small one on the right? If that's a skylight, why isn't the line above them also a skylight? I had a laser, so why isn't that thing also a skylight? Okay, they know, they have a lot of experience with defining them. But even supposing these are the ones, how about these ones? Are they also skylights? They are, but they're of a different type. So then if you didn't do a lot of work in advance to define what your classes are, now you have to go back and relabel all the data, say, oh, we've actually missed these ones. And then it's also important how you label them. Do you label them all together? And then if so, you missed the ones in the middle, which is like smallers. And oh, you need to label also these ones, then it's better to label each and every single one of them. So again, I want to highlight with this that when you need very specific data knowledge, then it's important to define it well in advance. It's not enough to just try and do it on Amazon Mechanical Turk, and then you've wasted a lot of time and a lot of money on gathering labels which are not so useful. So with this tool that the risk engineers have, that they can highlight stuff that they look at and they consider risky, we managed to get a decent data set. Okay, it's not deep learning size, but we have a few hundred labels that allows us to at least do some good model validation. And since it is well integrated in their daily workflow, they can continue to provide these labels as they work. It wasn't like a 1 week effort to just give us the labels. Cool, so we have the data. Now what? Now the next part is the model. In our case, the model is rather classic by now. It was in 2017, the classic faster RCNN. It consists of, yes, I see a lot of people nodding, a feature extractor and then two heads that predict the bounding boxes and the location and the classification of these bounding boxes. All said and done. So we have data, model, now we need to train it. And you probably are familiar, convolutional neural networks need a lot of data, and if just so, we have a few hundred examples. So there are many ways in which you can train these algorithms. You can go into domain adaptation, for example, to transfer between different domains, or there was also meta-learning, when one model helps the other one learn. But we found a recent paper that makes it much more easier. It's called frustratingly simple low-shot object detection. And the authors provide an insight that if you train on a base domain, it suffices to apply then transfer learning only on the head. So you keep the feature extractor frozen, and then you train with the previous and the new labels, only the box regression and the box classification. So this allows them to then push the state of the art with few-shot object detection by some 20 percentage points. Really nice paper, really well written, so I recommend it. Cool. So then we have data, model, training procedure. Then we're in applied machine learning days, right? Can we apply some AI? You're all probably familiar with this comic from XKCD, you know, where it says you put the data in and then you have answers on the other side, and then you have this big pile of linear algebra in the middle. And then if the answers are wrong, the author argues it's enough to mix this pile of linear algebra, which is why he has a shovel. It's quite tempting to think of it, but what's weird is that this is not exactly data science, this is model science. So I want to bring back the focus to data science and to say, well, data is actually really important. It's not so much about mixing the model in the middle. The authors proven that that works well. It's important to get the right data. So the promise of transfer learning is that convolutional neural networks learn pretty general features. So this example from AlexNet when it first came out is classic, everybody has seen. These are the first filters that the neural network learns. And then more recent neural networks also learn more advanced filters. They could learn edges, they could learn textures, they could learn patterns such as bubbles and rectangles and circles and how they combine together to do the prediction. It's important to know, however, that they also learn object parts. So they could also learn about eyes, they could learn about snouts, they could learn about genes, so then to see how these combine together. So in our case, it made then some sense that when our pre-trained model was trained on ImageNet that has cats and some 30 classes of dogs and airplanes, it wouldn't work that well on satellite images. Okay, there is quite a wide domain gap in between, and no amount of model mixing would suffice to get this problem to run. So if you realize that, and then you can start training on a related task. So we picked one of those 123 data sets that was available on Kaggle as a pretest task. Then we trained our own object detector afterwards. Actually, we fine-tuned, and then it started to learn. How do we know that it works? Well, we've used as an evaluation metric the mean intersection over union. This is also called the Jacquard index, and there are some examples here of how it works. Some people are used to say, okay, 90% something is like good, if you think about accuracy. We think that for IOU, sometimes even 70% is good enough, which is the example in the middle. And if you just look overall, then even the poor one that is considered poor at 40% provides good enough intelligence because it allows you to at least count the objects even if you're not fully covering them. So we've used this metric and we've seen that it works pretty well. And if we compare with the model that was pre-trained on ImageNet, not only this model trained on satellite images starts to learn faster and learns better, but then it learns much later on into the training as well. So in our case, we noticed that the ImageNet started to stabilize too soon, whereas the other kept learning. I've cropped the curve to put an accent into this part, but it started to learn quite well. Cool. So using these simple techniques, frustratingly simple techniques, and making attention to the transfer learning problematic, we've been able to train 3 different detectors and 1 segmenter. We've got decent results. We are managing then to count cars on commercial sites. We're able to count towers, cooling towers, and silos that could pose high risks to insurance. And also we're able to count the surface area of photovoltaic panels. And combining these with the previous work of the footprint, where then we can do a lot of statistics on these sites. So we can know 50% of the buildings are covered with solar panels, 30% of them have a dangerous amount of silos next to them, and so on and so forth. So this is mostly, yes, the lessons that we can learn, that we can really use all these techniques to better understand the risk. We can work with the experts to have a very well-defined data annotation procedure, and we can provide them with tools that integrate in their daily workflow in order to capture this specific knowledge that they have and then use it into aiding them to focus their attention on the objects that are really interesting to them. I'm then happy to take any questions. Thank you.
Thank you very much. Do we have questions?
There's one over there.
Yeah, we have a question over there. Great.
Thank you for the talk. It was very interesting. I'm a PhD student in EPFL. I would like to ask you, so you are using this evaluation metric which evaluates how well you find this cooling tower or silos, etc. But did you also evaluate if you can find the silo or cooling tower in the image for sure?
No, we haven't looked at that. We the data set is quite small, so that would be maybe the problem of recall, you know. So how many of the sites do we actually find the cooling towers? In terms of just verifying the model, we've set with IOU, which captures a little bit this information, because if you cannot find him, then you have 0 IOU, so it drops your metric a lot. But we didn't look at the number exactly. Would be a good point.
Okay. And how does this method is deployed to help the experts right now? Like they are using it like just to see the results, and they do it manually afterwards?
So currently, it's not fully integrated in their workflow in production. So they could run on a specific site. The ambition then is to pre-scan all the list in advance, and then they could look at the sites where they have the highest number of, I don't know, cooling tower, solar panels. But we prepare to do that by the end of the year. Thank you. Yes.
So I also wanted to ask a question. So you are counting the cooling towers and so on, but then there are probably different sources of those. So like, how do you like compare between them? And is it really just a good metric to use like number of cooling towers and solar panels? So is it just like only using these metrics? Is it sufficient to like get a good estimate, or like does it even make sense?
Yes, I understand. So. It's not a good metric to provide a risk factor. So we haven't said, okay, if you have 10 cooling towers and 90% coverage of solar panels, then you have a high risk. No, these are just to support the risk engineers. So it's more of a case of human-in-the-loop AI. Okay, this is not to take an automatic decision and to say, okay, this client, it has very good risk, we insure them. The other one, no, they have too many cooling towers, we don't insure. No, this is just to say, out of a list of 1,000 examples, we only have limited time to look at some of them. Which one should we look at? Should we look at the largest ones? No, we should look first maybe at the one that has the most cooling towers, if that makes sense for that industry. If it's a different industry, it may make sense to look at the solar panels. So it's only to support the risk engineers in their assessment, but then they take into account a lot of other different factors. Very good point. Yes.
You mentioned at the beginning that you have the area of the property. You're using that to avoid noise with neighborhood buildings. Do you exclude like 100% false positive in that sense? Is that enough to eliminate the case of, I don't know, a neighbor building something risky? Like, does it affect your evaluation if you have, you're basically excluding
yes, indeed. So these numbers that I've provided on the previous slide were raw model performance, but you are right. This would be a post-processing step that actually pushes the metric a lot further. Exactly, so we're excluding all the false positives. It's super useful, but I haven't recalculated the numbers by using the post-processing. Thanks, good point.
Maybe I can ask one last question while the next speaker can already set up. If I understood correctly, for training, you had to take another data set where you had supervised information so you could train a classifier, right? And then fine-tune that classifier for your setting. Have you experimented with instead keeping the same data set that you have, but pre-training it, let's say, in an unsupervised way where you don't even need any labels?
Very good point. It's exactly the point of my research for the rest of the year. Not yet.
Great.
So yes.
I'll give you my, for future ideas, I'll give you my account number.
Thank you very much.
Okay, so thanks again to the speaker, Ciprian.
Thank you.